Okay, so our starting point for today's lecture is these two equations that should be visible on your screen. So the state space of this angular momentum operators is such that I'll remind you that alpha is the eigenvalue of j square and beta is the eigenvalue of j3. And it is such that for a given alpha, there is a range of beta values that are allowed, and you can keep going up or down in beta values by applying j plus or j minus. But you cannot keep going indefinitely up or indefinitely down. This ladder has both a top rung and a bottom rung. And the top step of the ladder is such that j plus acting on the topmost state should be equal to 0 because there is nothing to do beyond that. And similarly, j minus acting on the bottommost state should be equal to 0. So we're calling the bottommost state having an eigenvalue beta min of j3, and the topmost state has an eigenvalue beta max. And I'll remind you that this comes from the constraint that alpha minus beta square is greater than or equal to 0. So let me box this constraint. Okay. All right. So now we will investigate the consequences of these two equations and try to understand what this tells us about beta max and beta min. So remember that j plus acting on alpha beta max equal to 0. And on this equation, I will apply j minus on the left. So we'll just do some simple algebraic manipulations for now. So I'll apply j minus. Of course, j minus acting on 0 on the right hand side is obviously equal to 0. So this equation, if j plus acting on alpha beta max is equal to 0, anything acting on that particular combination, that particular state is also equal to 0. So I might as well act j minus on it. And now let me substitute the expressions for j minus and j plus and investigate what this equation gives me. So this is, excuse me, j1 minus ij2 times j1 plus ij2 acting on alpha beta max equal to 0. So let us look at this particular combination. And you will be doing calculations of this sort many times. So please be careful in doing the multiplication here. So the first term here is j1 square. The second term is plus I j1, j2. Remember that j1 and j2 do not commute, so you should be very careful about the order. The third term is this multiplying this. So that will be minus I j2, j1. And the fourth term would be minus I square j2 square, which will be plus j2 square. Okay, so I can write this whole thing as j1 square plus j2 square plus I times j1 j2 minus j2 j1, which is basically the commutator of j1 and j2. Okay, if there's any questions about any of these simplifications, please stop me and ask. And since j square is j1 square plus j2 square plus j3 square, I can write j1 square plus j2 square as j square minus j3 square. So putting everything in this expression, I finally get j square minus j3 square plus I times the commutator of j1 and j2, this particular combination of operators acting on the state alpha beta max equals 0. Okay. Now the reason we did everything in terms of j square and j3 square and not in terms of j1 and j2 is because we know how j square and j3 square act on these states. So j square acting on alpha beta is alpha times alpha beta, and j3 acting on alpha beta is beta times alpha beta, right? Okay. So this tells us j square acting on alpha beta max will give me alpha minus j3 square acting on alpha beta max will give you minus beta max square plus I times, okay, actually let me do it in two steps so it's slightly easier. So this is j square minus j3 square. So the commutator of j1, j2 is ih bar j3. So this will become minus h bar j3 acting on alpha beta max equal to 0. Okay, where I have used the fact that commutator of j1, j2 is ih bar j3. So now act all these guys on the state alpha beta max. The first term gives you alpha. The second term gives you beta square. And the third term gives you h bar beta acting on alpha beta max, excuse me, equals 0. Okay. Now the only way this can be equal to 0, since I know that the ket is non-zero, the only way this can be 0 is if whatever is multiplying it is identically equal to 0. So this tells me that alpha, sorry, this has to be beta max, yeah, because that is the eigenvalue of the state alpha beta max. So this tells me that alpha minus beta max square minus h bar beta max equal to 0, which tells me that alpha equals beta max times beta max plus h bar. Okay. So this is my first conclusion, and this stems from the fact that there is a topmost state and J plus cannot act on this topmost state. And the rest is just simple algebra. I simply manipulated it because I did not know how J1 and, well, I have not yet figured out what C plus and C minus are. I don't want to use only J plus, but the combination J minus J plus or J plus J minus, they can be written completely in terms of J square and J3. So I used this fact to write this in terms of J square and J3. And this gave me a very simple relation between alpha, which is the eigenvalue of J square, and beta max, which is the maximum eigenvalue of the J3 operator. Okay. Similarly, I will use the equation J minus acting on alpha beta min equal to 0. And now I will act both sides of this equation. Since I have not figured out what C minus is yet, I will act both sides of this equation by J plus. Okay. And then I can follow the same strategy, J plus J minus. I'll substitute, and J plus J minus will turn out to be equal to J square minus J3 square plus H bar J3. And if I do this simple calculation, which you should do, so I will let you complete the steps. Which is identical to the former calculation we just did. And this will give you alpha equals beta min times beta min minus h bar. Okay. So remember that alpha is related to the maximum value of J3 via this relation, and alpha is related to the minimum value of J3 by this relation, but it is the same alpha that we are talking about, because as we just discussed, J plus and J minus do not change the value of alpha. They don't change the eigenvalue of J square at all, because as we discussed, J square is rotationally invariant. We'll come to this later. They simply push the value of beta up or down by units of h bar. So let me equate both the right hand sides of this equation, and since both are equal to alpha, I have the equation beta max times beta max plus h bar equals beta min times beta min minus h bar. Okay. So let's clean up this equation and try to understand, since we do not know what the maximum value of beta is and what the minimum value of beta is, let us try to figure out how they are exactly related, because this is after all a quadratic equation in beta max, and I should be able to figure out a relation between beta max and beta min. So I'll clean up this equation, beta max square minus beta min square, because it's a beta min square on the right hand side, I'm going to put it to the left. Plus h bar beta max plus beta min equal to 0. Okay. So I'm going to solve this equation to tell me how beta max and beta min should be related. So obviously, this guy is beta max minus beta min, a plus b, a minus b, right? So if you use that, you can take beta max plus beta min as a common factor from both these terms. So beta max plus beta min times beta max minus beta min plus h bar equal to 0. So this is factored easily into two terms, the product of which is equal to 0. And the only way the product of these two terms is equal to 0 is if either one of them is equal to 0. This is how you solve quadratic equations in general. So this gives you two solutions. Beta max equals minus beta min, or beta max equals beta min minus h bar. Okay. Now, if you look at these two equations, you realize that the second solution is not physically acceptable. It is not because you go from beta min to beta max in steps of h bar. So by construction, beta min is smaller than beta max. But the second equation seems to say that beta max is smaller than beta min by 1 unit of h bar. So this solution is not physically acceptable because it violates the rules of our construction. So the only possibility is that the minimum value of beta is equal to just the negative of the maximum value of beta. So let's go back to our ladder. So in this ladder, what do we have? We have, there is a maximum value of beta, and to come down this ladder, I either apply J minus and then keep going down in steps of H bar, right? So if you look at it this way, now we have a connection between the maximum value of beta and the minimum value of beta, okay? So let us draw this ladder again. So I have alpha beta max, okay? And then I apply the J minus operator and I go down to alpha beta max minus h bar, alpha beta max minus 2h bar, and I keep going till I get a state alpha minus beta max. Okay, this is the state space. So then how many different steps I take? I do not know, right? So to go from beta max to beta minus beta max, which is beta min, I have to take some number of states. It's obviously an integer number because obviously it's going from the topmost state to the bottommost state. So let me say that I take n steps of h bar to go from beta max to beta min. So let us say we take n steps of h bar to go from beta max to beta min. And I remind you that beta min is minus beta max. Okay, if beta max is 5, beta min is minus 5. Then this tells me that the difference between beta max and beta min is n times h bar, because I've taken n steps of h bar to go from beta max to beta min. The difference between them should be n times h bar. Okay, but since beta min is minus beta max, this tells me that twice beta max is nh bar, and this tells me that beta max is nh bar over 2. And this n could be anything. I do not know what this n is. It could be just 0 step, which means there is only one state in the spectrum. Or it could be 2 steps or 5 steps or 15 steps or 27 steps. I do not know. I've not figured out what the value of n is yet. We'll talk about that in a second. But some integer number of steps have to be taken, and the value of beta max is nh bar over 2. Is this clear? Which also tells me that beta min would be minus nh bar over 2. So alpha, which is beta min times beta min minus h bar, or beta max times beta max plus h bar. Alpha would be equal to, substitute the value of beta max that we just found out. This is nh bar over 2 times nh bar over 2 plus h bar. Okay. So this alpha value is equal to, I can pull out the h bar. So h bar square times n by 2 times n by 2 plus 1. Okay. So now I'm going to employ a slightly different notation. This is the standard notation employed in the angular momentum studies and algebra. And I'm going to call this n by 2, which appears both in the definition of alpha and the definition of beta. This n by 2, I'm going to, so I'll actually be specific here. Change of notation. I'm going to call this n by 2 as j, the angular momentum of the state. Okay. And instead of labeling the state by alpha and beta, I'm going to label it by j and m. So instead of beta, I'm going to call, so alpha, I'm simply going to, so in that case, beta max is j, beta min is minus j times h bar and minus j times h bar. And we go from beta max to beta min in units of h bar, which means the beta I'm going to rename to m. Okay. And alpha is equal to h bar square. If I rename n by 2 as j, this is j times j plus 1. Okay. So now the state space is such that j square, instead of labeling the states as alpha and beta, I have changed my notation. Instead of alpha, I will use j. Remember that j itself is not the actual eigenvalue of the state. The actual eigenvalue of the state is h bar square times j plus 1. But j is just a way to label the state, that is so. So j square acting on jm is h bar square j plus 1 jm, and excuse me, j3 acting on jm, I'll call this as mh bar acting on jm. Okay, such that the maximum value of m is plus j and the minimum value of m is minus j. So for a given value of j, for a given value of j, whatever that value is, m can range, or not can, m ranges from minus j to plus j in steps of 1. Okay. So if n goes from minus j to plus j, so let us say that, okay, we will come to this in just a second. Now let us make another point about the value of this angular momentum j. The value of this angular momentum j is n by 2. Remember that j is n by 2. And n can be anything, right? So you take just one step and get to the bottommost state, or maybe there's just one state. Or if there is two states, you take one step to go from the top to the bottom. If there is three states, you take two steps to go from the top to the bottom. So n can be 0, 1, 2, 3, anything, which means j can be 0, 1 half, 1, 3 half, 2, whatever. Okay. So notice that unlike the case of orbital angular momentum, in the case of total angular momentum j, you not only have integer values of j, but you also have half integer values that are allowed. Okay, so this is the fundamental difference between our discussion on L and our discussion on j. We at least vaguely motivated that this could be written as L plus S, right? So, well, not vaguely, but not very rigorously motivated that it should be L plus S. We will make this more precise when we talk about angular momentum H. Okay. So unlike an orbital angular momentum, the total angular momentum J can take either integer values or half integer values. Okay. So it is a fact of nature that there are particles which have an intrinsic angular momentum, not orbital angular momentum, but an intrinsic angular momentum. And this intrinsic angular momentum, called the spin, can be whatever value it wants. So let us say that it can be an integer value of spin. There is like spin 1 particles. These are called, for example, bosons. An example of a boson, fundamental boson with spin 1 is, for example, the W boson and the Z boson. There is also fundamental particles with spin 0. These are called scalar bosons. An example is the famous Higgs boson. And there is also particles with spin 1/2, like the electrons and the other fermions. And there is also an example of particle with spin 2, which is the graviton. Of course, we have not yet found a particle with spin 3/2 unless supersymmetry comes along and is proved experimentally. Okay. Anyway, so this is the fundamental difference between the total angular momentum J in particular because of the spin contribution and the purely orbital angular momentum, where the m value, as we discussed, has to be an integer. So in this case, m value can be both integer and half integer. Okay. So we still have not completely finished this discussion. We still have to understand how J plus and J minus act on this state, but we are getting very close to understanding the structure of the Hilbert space, right? So let us actually do a couple of examples to make this point clear. So let us say that we are talking about a physical system with J equal to 0. Sorry, I have to stop share and reshare again. Give me 1 minute. Okay. So let us say that we are talking about a physical system with total angular momentum J equal to 0, which means m can go from minus J to plus J, but in this case, since J is 0, m can also be only 0. Okay. So this means that there is only one state possible with J equal to 0 and m equal to 0. Remember that the state is characterized by the J value and the m value. Now, what if J equal to half? In this case, m can go from minus J to plus J in steps of 1. So m can be minus half or plus half. So in this case, you have two states. The topmost state is 1/2, 1/2. And the bottommost state is 1/2 minus 1/2. There is no other state possible because m should go from plus J to minus J in steps of unity. So what if J equal to 1? In this case, the topmost value of m is plus 1. The bottommost value is minus 1. So it should go from plus 1 to minus 1 in steps of 1. So it goes from 1 to 0 to minus 1. So in this case, m is 1, 0 or minus 1. So you have three states for J is equal to 1. So you have the topmost state, which is 1, 1. Then the middle state, which is 1, 0. The bottommost state, which is 1, minus 1. And then you can keep going like this. So J equals 3/2. M should go from plus J to minus J in steps of 1. So this can be 3/2. And 3/2 in, if you take off 1 from 3/2, you get 1/2. If you take off 1 from 1/2, you get minus 1/2 and then minus 3/2. So this will have 4 different states. So you'll have 3/2, 3/2, 3/2, 1/2. 3/2 minus 1/2 and 3/2 minus 3/2. Okay. So the J is equal to 0 system would be a one-dimensional linear vector space. The J equal to half would be a 2D linear vector space because there's only two different basis vectors. The J is equal to 1 would have 3 basis vectors, so it's a 3D linear vector space. and j equal to 3 halves would be a 4D linear vector space. So there is actually an interesting, easy way to understand the dimensionality of the Hilbert space given the value of j, because given the value of j, m can go from plus j to minus j in steps of 1. So ms plus j minus 1 all the way to minus j plus 1 and minus j, right? And m can take, if we count the total number of values between plus j and minus j in steps of 1, you will get 2j plus 1 value. Okay. So the dimensionality of the Hilbert space for a given value of j is basically 2j plus 1, which you can easily verify. For j is equal to 0, 2j plus 1 is 1. For j equals half, 2j plus 1 is 2. For j equals 1, obviously 2j plus 1 is 3, and so on and so forth. So this is the dimensionality of the LVS for the specific value of j. Okay. Are there any questions about any of this? Any questions or any comments? Is it okay?
Sir, what do you mean by the dimensionality of the LBS of which system?
So let us say that you have some system that has a total angular momentum 3 half. Okay. Then to understand this system, the angular momentum of the system and the associated action of other observables of the system, etc., I have to construct the Hilbert space of the system, right? That is our first step. So if I construct the Hilbert space of the system, I should construct a 4-dimensional Hilbert space if the system has a total angular momentum of 3 half, because there is 4 states possible. So the particle can exhibit itself in 4 different states. It can the particle can have an m value of 3 half or 1 half or minus 1 half or minus 3 half. No other value of m is possible. So I am claiming that the J3 value is such that it is quantized, of course, in units of h bar, and it has a maximum and minimum value corresponding to the value of j that we are talking about. So the dimensionality of the Hilbert space refers to simply what is the total angular momentum of the system that we are talking about. So let's say that you have only one electron. It has some orbital angular momentum and it has a spin angular momentum of half. So we have to construct the total angular momentum. We will understand how to construct this. And let us say that the total angular momentum of this guy is some value, let us say 1, then you would have to look at a 3-dimensional space to understand the dynamics of this particular electron. Suppose if you have 2 electrons, both of them have both orbital and spin angular momenta, then you have to add the angular momenta carefully. So you have to add the orbital and spin of one and orbital and spin of the other, and then add the 2 total momenta together. And whatever this value is, you will construct the state space accordingly. Let us say that you get the total angular momentum for the system to be 5, then it will be a 11-dimensional linear vector space. So because it is 11 possible values of m for this particular system. Okay. All right. So the last thing that remains is to understand how j plus and j minus act on this particular. So there is one question. A system can consist of more than one particle. If one particle has j value different from the other, how do we define the dimensionality? This is a good question. We'll answer this when we talk about addition of angular momenta. So let us say that you have an electron. You have 2 particles, particle 1 and particle 2. Particle 1 has total angular momentum 1 and particle 2 has total angular momentum half. Okay. Then the addition is not very simple. I simply cannot simply add the 2 angular momenta. There is specific rules as to how to add the angular momenta. But let us say that I add the total angular momenta and the total angular momentum comes out to be some value. Okay, and I will take that value as the total angular momentum and then construct the Hilbert space of the system accordingly. So it will not be the Hilbert space of the first one or the second one, but it will be the Hilbert space of the total one. So now the question is, how is the Hilbert space of the total particle, the two particles related to the individual one particle Hilbert spaces? This I will answer carefully next week, because next week I will spend some time, at least one lecture, to basically tell you the difference between what are called tensors products of uh, Hilbert spaces. There is some mathematics involved here that we have not talked about yet, because we have not talked about multi-particle systems. But I'll clarify this next week when I talk, before I start talking about addition. So the question is, how is the dimensionality of the entire particle system related to the dimensionality of each of the subsystems? Any other questions or comments?
Sir,
Yes. So,
sir, here when we say the dimensionality of this LVS, so does this LVS, the LVS should be the Hilbert space of the particle should contain every vector, right? The energy eigengets and the other eigengets, okay, the
absolutely.
like position gates, cats. So how do we know that um, the number of this other observable quantities, these also coincide with
No, so
our
you should be careful in understanding. So the Hilbert space that you construct depends on the problem you are trying to solve and the questions you are trying to ask, right? So let us say that I'm looking at a problem where there is a system of particles, but the Hamiltonian is rotationally invariant. Now it makes sense for me to construct a Hilbert space such that I'm looking at the simultaneous eigenvectors of the Hamiltonian and the angular momentum operator, right? So now, so let us say that I have this Jm, and these are the angular momentum operators. Now I'm careful, if I'm careful, these vectors, if I'm talking about a rotationally invariant problem, these vectors would also be the eigenvectors of the Hamiltonian operator, right? But the dimensionality of the vector space would not change, because I'm talking about simply the 4 vectors or 5 vectors depending on what the j value is. But of course, the j and the m values alone will not characterize these states. I should also, for example, talk about what is the energy of these states, right? So there could be other eigenvalues that come along for the ride, and this kit Jm would probably not be a complete description. I could probably put another eigenvalue of whatever observable I'm talking about, right? See, the choice of the Hilbert system, Hilbert space is up to you. What you should choose, whatever Hilbert space is most convenient for this problem. Now, in all angular momentum problems, it makes sense to choose a Hilbert space which is a simultaneous eigenvector of j square and j3, as we have discussed, because it makes all your angular momentum operations very easy. Now the question is, how do other operators act on this Hilbert space? Now, if I have a rotationally invariant problem, like the hydrogen atom, then the H does not, so if I go from, let us say, 3 half to 3 half, 1 half, if I'm talking about a rotationally invariant problem, the energy does not change. That is the whole point, right? But there could be some other observables that change. I do not know. I cannot talk about, I cannot construct the simultaneous eigenvector of every possible operator in the universe, right? Because they don't commute, obviously. But my job is to collect everything that does commute and talk about a simultaneous eigenvector of that particular subset, the complete set of commuting operators. And because the action of these operators on this vector space, for example, is very simple. Of course, this doesn't mean that the action of other operators on this vector space is also simple. They will give you some random uh, linear combination of all these states. For example, I have a random operator Q and I act it on this particular state, it will give me some linear combination of all the 4 states. This doesn't tell me that my choice of this states is wrong or incorrect. It simply tells me that I simply cannot take as a simultaneous eigenvector of every possible operator in the universe. So once I fix my Hilbert space to be the angular momentum basis vectors, then I would have to ask what are the other operators that possibly act on this and how do they do it? That is a different question. And to understand that question, I might have to understand how, for example, if there is a new operator, if there is some operator O that acts on, let us say JM1 and gives me some, say K times JM1 plus K2 times JM2, then so be it. Oh my gosh, it's not showing again, sorry. Just give me 1 minute. Okay, so there could be an operator that mixes these angular momentum eigenstates in this particular fashion. That is totally fine. And it could also happen that J and M are not enough to characterize these states. I might have to include other eigenvalues of other operators also. That is also fine. So suppose if somebody tells me you have to talk about this operator also and tell me how this operator acts on these 4 or 5 or 6 or whatever states that you're talking about, fine. I will take that operator and ask how it acts on these different states and then do it methodically. But this doesn't change the fact that the dimensionality of the vector space for a specific value of j is fixed, and that is just 2j plus 1. Does that answer your question?
So, sir, then does that mean like suppose like we have these two operators, this angular momentum operator and Hamiltonian, which commute. Okay, suppose two operators that commute and we take the simultaneous eigenstates of those and construct a Hilbert space. Now suppose there is this another operator which doesn't commute with either of them.
Correct.
So if I want to get the expectation value of that operator, then do I have to construct another Hilbert space?
No. See, so you have a choice, right? So what is the fundamental question that you're trying to answer? So let us say that you have H, you have J square, and you have another operator A. And let us assume that A is not rotationally invariant. And A doesn't commute with the Hamiltonian also. It is not a conserved quantity, right? You have some operator like this. Now, always my fundamental guiding principle is that I will choose to work in that Hilbert space in which the action of most of these operators is easy. So in my case, if I have a rotationally invariant problem, then H and J square commute, and I will take as my Hilbert space the simultaneous eigenvectors of H and J square. Okay, so in this case, it will be the Jm. Okay, so now the question is, if it is rotationally invariant, how does H act? Remember that, let us say that H and J3 is also equal to 0. Okay, suppose if I have what is it called, azimuthal symmetry. Okay, then I will not change my energy values as I go from one state to the other, Jm to Jm prime. If I go from one to the, because H commutes with J3 operator, I can always choose the axis of rotation to be along J3, then I will say that H acting on Jm and H acting on Jm prime would be the exact same thing. It will give me the exact same value of energy. So energy will not change as I move from one of these states to the other state. Okay, which means there is a degeneracy in the problem. This is what exactly we talked about last semester also. Symmetry always implies degeneracy. Okay, in this case, if there is a rotational symmetry, then let us be specific and talk about, let us say, spin half, right? There is two states, 1/2, and 1/2 minus 1/2. So if there is a rotational symmetry in the problem, then H acting on this state would be this, and H acting on this state would be the exact same energy. So these two states would be degenerate. So this means that if I simply measure the energy of the system and I get 10 joules, I really cannot say if there is one state, if I'm measuring the energy of this state or that state. An energy measurement would not be a good discriminator to tell me which state I'm talking about, because there is degeneracy in the system. So how do I lift the degeneracy in the system? I will lift the degeneracy in the system by measuring something else that doesn't give a shit about rotations. If something else breaks rotations explicitly, and if I measure that particular operator, then that operator might be able to distinguish between the 1/2 state and 1/2 minus 1/2 state. Okay. So later on we will understand time dependent perturbations, and this is exactly what we would do. We will try to break the degeneracy of the system by applying some operator that doesn't respect the rotational symmetry. Okay. So the 2 points that are important is that first point is always choose the maximal set of commuting operators and construct your Hilbert space. If you have any other operator that doesn't commute, that is fine. So A acting on Jn. So for example, A acting on 1/2 would give me some A1 1/2 plus A2 1/2 minus 1/2. And that is fine. This is a necessary evil. Oh my gosh, my Bluetooth is severely problematic today. I don't know why. Okay. Okay. So this is totally fine. So you simply choose the maximal set of commuting operators and construct your Hilbert space. That is all. Does it make sense?
Yes, sir.
Okay. All right. Have I talked about C plus and C minus before? Yeah. Okay. So I have talked about C plus. Okay. So remember that we discussed that J plus and J minus increase or decrease. So J plus acting on alpha beta, we said was some C plus, which is a function of alpha beta times alpha beta plus H bar, right? So in our new notation, this relation becomes J plus acting on Jm is some function which is a function of J and M times Jm plus 1. Similarly, J minus acting on Jm is some function which is a function of J and M times Jm minus 1. Okay. Now we have to understand how these states are normalized. So for a given value of J, I can go from plus J to minus J in steps of H bar, in steps of 1. And since these are eigenvectors of a Hermitian matrix, they are automatically orthonormal. So if I fix the value of J, then I find that Jm prime has to be delta M prime M. Okay. Similarly, if J is also the eigenvalue of a Hermitian operator, so it should also be orthonormal with respect to the J index. So if I have a J prime M and a Jm, this should be equal to delta J prime J. Okay. So usually we can combine both these guys into one simple equation, since they are both eigenvalues of Hermitian operators. J prime M prime Jm equals delta J prime J delta M prime. Okay. So again, for the spin half case, I will have 1/2 overlapped with 1/2 would be equal to 1, but 1/2 overlapped with 1/2 minus 1/2 would be equal to 0. Okay, so this is the orthonormality relation for the kids. Okay, so we'll use this to understand what C plus and C minus should be, and then we will. I thought we will work out the spin half matrices in class, but we will work it out in the tutorial. I think that's also okay. So J plus acting on Jm is C plus times Jm plus 1, right? Now let us take the dagger of this equation. Now J plus is J1 plus IJ2, and J1 and J2 are all Hermitian, which means J plus dagger would be J1 minus IJ2, which is J minus. So if I take the dagger of this equation, I will get excuse me, Jm, J minus equals Jm plus 1 C plus star. C plus is some complex number, so if I take the dagger, I should only take the complex conjugate. And I'll multiply these two equations together. If I multiply these two equations together, I get Jm, J minus, J plus, Jm equals C plus mod square times Jm plus 1, Jm plus 1. And since this is the overlap of the state with similar values of J and M, this is equal to 1. So this gives me a convenient formula to evaluate my proportionality constant C plus square. This is equal to Jm. Again, J minus J plus is J1 minus Ij2 times J1 plus Ij2. So this would be equal to J square minus J3 square. Refer to our previous calculation, minus H bar J3 acting on Jm. So J3 acting on Jm would be MH bar. So this gives me Jm times H bar square J plus 1 minus M square H bar square minus J3 acting on Jm would be MH bar. So this gives me MH bar square acting on Jm. Of course, everything inside is just a number, so I can write this as H bar square J plus 1 minus M square H bar square minus MH bar square. And this gives me a very convenient formula. This is H bar square times J into J plus 1 minus M into M plus 1. Okay, now I have, this is just a formula for mod of C plus square, which means C plus can be some phase times this, but usually the convention we choose is that we just set the phase equal to 0, phase equal to 1. So I can write C plus as the positive square root of this guy. So C plus I will choose to be H bar times square root of J plus 1 minus M plus 1. Okay, and similarly, J minus acting on Jm, which is C minus times Jm minus 1. And we can figure out using very similar calculations that C minus is H bar times J plus 1 minus M minus 1. Okay. So this tells you how these J plus and J minus act on this linear vector space. So remember that in this basis set Jm, the matrix form for J square will be diagonal because Jm are the eigenvectors of J square. The matrix form for J3 will also be diagonal because Jm is also an eigenvector of J3. But the matrix form for J1 and J2 will not be diagonal. So in fact, we can work out what the matrix form for J1 and J2 will be. So let us look at the matrix element. Matrix element of, let us say, J1. So what is J1? I can write J1 as 1/2 J plus plus J minus. Okay. So let us look at the matrix element for J1. So J prime, M prime, J1, Jm. What does this give me? So this is equal to 1/2 J prime, M prime, J plus plus J minus Jm. Okay. Now let's piece this up into two different numbers. The first number is 1/2 J prime, M prime, J plus Jm plus 1/2 J prime, M prime, J minus Jm. Okay. And J plus acting on Jm would give me C plus times Jm plus 1. So this is equal to 1/2 C plus, which is H bar times J plus 1 minus M plus 1 times J prime, M prime, Jm plus 1 plus 1 half. J minus acting on Jm would be C minus Jm minus 1, which is minus mm minus 1, the overlap of J prime m prime and Jm minus 1. Okay. So this overlap of these two vectors is non-zero only if J prime is equal to J and m prime is equal to m plus 1. Similarly, this overlap is non-zero only if J prime is equal to J and m prime equals m minus 1. So I can write down the matrix elements of J1 as H bar over 2 and delta J prime J, I'll pull out. This is equal to square root J plus 1 minus m plus 1 times delta m prime m plus 1 plus square root of J plus 1 minus m minus 1 delta m prime m minus 1. Okay, so you can clearly see that the J1 matrix will not have any diagonal components because in the Jm basis, J1 is not equal to 0 only if m prime is greater than m or by 1 unit or less than m by 1 unit. So there will be only off diagonal components in J1. So similarly, work out J2. Work out J2. Okay. And you will again find that J2 only has off diagonal components. Remember that J2 is 1 over 2i times J plus minus J minus. Okay, so J2 you can clearly see would be also imaginary. It will be purely imaginary because all these numbers are real numbers. So it's multiplied by 1 over 2i. So obviously J2 matrix is going to be an imaginary matrix. Okay. So we will apply whatever we have learned here to the example of spin half and we will do that in a tutorial problem. For now, we will stop and please take stock of what we have done. We have basically figured out the structure of the Hilbert space of these angular momentum operators. Of course, we will continue this discussion a little bit in the tutorial session also. And I will tell you a little bit more about how to actually construct it for a specific case. Okay.